Welcome to the session 2.9 of your chapter Optics. In this session, we will be discussing about refraction through a concave lens. In before class, we studied what is the applications of convex lenses and some application or for camera lens, magnifying lens, microscope, telescope, slide projectors, and finally correcting hypermetropia. Hypermetropia is a defect, and these are the applications or the uses of a convex lens. Now, starting from the today's session, refraction through a concave lens. A concave lens is actually a diverging lens. We all know that, and actually, we studied refraction through a convex lens in session 2.7. If you hadn't seen that video, just go back to the playlist and first watch that and then come here. Going with the paragraph, let us discuss the formation of images by a concave lens when the object is placed at two possible positions. First possible position is object at infinity. That means if you take the concave lens of focal length 5 centimeter, then a 100-meter object will be infinity for this lens, and that's what they are calling it as object at infinity. When an object is placed at infinity, a virtual image is formed at the focus. See here, it's a virtual image because when the incident ray is going to hit the lens, after that the lens is making the incident ray to diverge. So these rays won't meet at a particular point after they are diverged, right? So we need to provide or project the rays in backward direction, and the point where they are meeting is the point where the image is gonna form, and that point here is focus because the object is kept at infinity and the image is going to be formed at focus, and this image is a virtual image. And what is a virtual image actually meant? If you are going to see from here in this part, you will see that the object which is actually kept here, I mean, if you just going to keep a line, okay, a line or an arrow mark here, okay, when you see from this side, you won't be seeing that the arrow is actually placed at infinity. You will be seeing that arrow is placed here, and the actual size of the arrow is very small because they mentioned here the image is much smaller than that of the object because these rays are meeting at the principal axis, and there is no length, man, actually there is no length. See, I'm sorry, see here, the image doesn't have a size, and this meeting point and the principal axis do not have any intermediate distance. But if you take a look at this image, the meeting point and the principal axis is having some distance, and that distance is the image height. So we can say that this one, I mean this image is a bit taller or bigger than this one, and due to that they call this image as point image because it's very small. So if you're gonna see an arrow, it will be very small in the image from this side, but actually we kept the arrow at infinity, and that's why it is going to form at focus. This is the first case, we done it. And the second case, object anywhere on the principal axis at a finite distance. So first of all, you need to have a question: why we had 6 subcases in convex lens and here only 2 cases in concave lens? You must have this question. And for that, what is the answer is that in convex lens we will be getting two types of images. One is real image, which can be obtained in a screen, and for that a real image case is very different, so we are going to get five different cases. And the last one is actually a virtual image, and virtual image can't be obtained in a screen, and for that only one case, and totally it's six cases. But here, due to the diverging property of the concave lens, this concave lens can't provide any real image, and that's the reason why we are only studying two types of virtual image classifications. Going on with the second one, object in the principal axis at a finite distance. Finite distance means somewhat, if you take this lens focal length as 5 centimeter, then a finite distance will be 20 centimeter, 30 centimeter, 40 centimeter. That's the finite distance. When an object is placed at a finite distance from the lens, a virtual image is formed between optical center and focus of the concave lens. The size of the image is smaller than that of the object. Yeah, as you can see that this is the object which is kept at a finite distance before 2f. 2f is center of curvature, f is focus, and o is optical center. And here object is kept in between center of curvature and focus. Okay, and it is a finite distance, right? If focal length is 5 centimeter, then center of curvature will be 10 centimeter, and this object might be kept at some distance like 8 centimeter, something like that, right? So that is a finite distance. Object is kept at 8 centimeter, and that's a finite distance, and object size is AB, and here image size is A dash B dash. See, if you compare these two, you can definitely say that the image is smaller than that of the object, right? Yeah, that's what they are saying in the last line. The size of the image is smaller than that of the object. Okay, you must understand one thing. Why they gave two cases? They might have gave they might have given only one case for virtual image, right? But in the first case we saw a point image which is formed in the focus, but here there is no point image. The image is not going to be formed at focus. Instead, it is going to be formed in between focus and optical center, and the distance of the object is finite. That's the reason they gave two sub cases. That's all. Here also ray diagram is very much important, and you need to practice these ray diagrams for getting good marks in your physics. Then, but as the distance between the object and the lens is decreased, see, this is the object, right? And this is the in this distance is the distance between object and lens. And if you are going to decrease this distance, that means if the object is going to be placed at 2 or 3 or 4 or 5, then the distance between the image and the lens also keeps decreasing. See, wait. First of all, we will complete the paragraph. Further, the size of the image formed increases as the distance between the object and the lens is decreased. This is shown in the figure. Just take a clear look. It's very easy. Wait a minute. Okay. See, just remove all this 2, 3, 4, 5, and here also 2, 3, 4, 5. These are image, and these things are objects. So for the first case, we are taking the object at 1, and where the image is going to be formed is at 1. It is nearer to focus, and then we are going to take the case 2. We are going to bring the object to the second position, and that means we are going to decrease the object and lens distance, right? And if the object is kept here, then we will be seeing the image here somewhere, right? So here also the image and lens distance is decreased, and the second differentiation is the height of the image is keep on increasing. And the same, if we keep the object at 3, you will be getting the image at 3, which is much closer than 2, and it is much higher than 2, right? Then if we keep at 4, the image is at 4 and it is going to be taller. In 5, it is much closer and it is the highest or the biggest image you might be seeing, and that's what we are going to interpret here. They had interpreted actually. What they are saying is the size of the image formed increases as the distance between the object and the lens is decreased. That's all. That's the line which you need to understand and learn. And I guess that's all for today. We'll be doing applications of concave lenses in the next video. Until that, thank you. Bye bye. And a last thing, like it, share it, and subscribe my YouTube channel.